Okay, so we'll talk about distributed tracing as one of the ways of actually root causing the outages. We'll talk briefly about how it works, and we will look at multiple ways of like looking at the system behavior via distributed tracing lens, from one trace to many traces to many traces, etc. So just a quick note about us. I'm Yuri, and this is Joe. We work at Uber on the observability team, specifically on the Jaeger team. Jaeger is an open source tracing system that you can spin up and contribute to if you want to. Just before I start, as a quick poll, how many people are familiar with distributed tracing? Pretty much everyone, what you would expect, hopefully, from the Observability Practitioner Summit. So I'll be very quick about this. So today, many distributed systems are extremely complex, and there's a well-known facts like loading a Netflix or a Facebook page takes actually dozens of microservices, hundreds of nodes participating in it. And at Uber, we have over 3,000 microservices. It's one of the probably largest microservices architecture. And so this is kind of what it looks like in terms of connectivity between all the services. And then every time you push a button to get a car on Uber, something like that happens on the back end of the architecture. So there's, like, again, tons of different services involved. In fact, some of our pickup, I think, workflows involve 50 services, literally. And plus many of them like repeated many calls. So how do we, this happens like billions times a day, so if something goes wrong, how do we like know what's wrong, and how do you monitor this whole thing? And one of the difficult parts with microservices is that if you are an on-call person for some business workflows, it's very hard to know, well, which part of the system is actually misbehaving at this particular point. And until you find that part, you're in an outage. You can't resolve it because you don't know whom to page, and like you probably don't actually own that particular system that's failing. And so pinpointing that is a very effective way of reducing your outage time in reducing time to resolution. Like the stakes for that are very high, obviously. So there's like a study in 2016 showed that over 98% of companies responding to the study said that 1 hour of outages cost them $100,000, right? Whereas 1/3 of the companies said it costs from 1 to 5 million. And so if we can reduce even by like 20 minutes, there's like a massive economic value in doing that. However, the traditional monitoring tools that we have today, or you have built for the last 20 years, they don't really help with that. The metrics are very good at actually detecting outages, but they can't explain why there's an outage and what's causing it. And logs are just like almost completely useless with the microservices, and even if you aggregate them. So why they're not completely useless, but why these tools fail is primarily because they're looking at one node in your architecture, and they only tell you a small picture about that node, and you don't know what's the rest of the thing is doing. So it's like a debugging without a stack trace. You have an error at some point, but you don't see the whole path of what caused that error. And so what we really want to do is monitoring this whole transaction that goes through the microservices and be able to reason about it. And so I will skip the detailed explanation because most people understand how distributed tracing probably works. It's like we just propagate the context with some metadata through the call, and we record various informations that allows us to build, for example, a Gantt chart of the execution on the right side, and reason about timings, reason about errors and root causes, right? And so I will hand off to Joe to actually walk you through some examples of like what happens when we look at one trace, and then we'll go more advanced from that.
Hello. So I just want to say this is my first time speaking at a conference, and this is a really awesome conference to kick it off, so very happy to be here, and thank you for joining us. So Yuri talked about why we're interested in distributed tracing and kind of briefly about how it works. Now we're going to look at gaining value from our investment in distributed tracing. So here we have the trace timeline. It's basically a Gantt chart, and this is kind of a raw view of the trace data. We can drill in to get metadata, but this focuses on the timing aspects and the relationships, the parent-child relationships. So if we look over here on the left, we have a list of all of our spans and the service name and operation for the span, and indentation indicates the parent-child relationship. So this kind of is a way of viewing that graph. And if we look over here on the right, we have a time-based mapping. So this is where the Gantt chart kicks in. We can see the root node, the top node, extends for the full length of the trace. It's the full duration. Its child, its first child, is more than half. And so from this view, we can kind of sense sort of the timing of the parent-child relationships and the spans. So if we focus on this bar that's immediately above the 3 here, we can see that it's sort of a leaf node if we look on the left, and it's kind of determining the length of all the nodes above it. So we can infer 2 things. One, that this leaf node has all self-time, and that its parents are almost no self-time. They're waiting on this leaf node. And if we look at the rest of the trace, we can see that this leaf node is blocking the progress. It's a blocking operation in our transaction. It's also quite long. It's over 500 milliseconds. So we can infer or determine that this is probably an interesting place to look to optimize our system, because it's blocking many things and it's quite long. So over here we have the operations that follow that operation. And we can see this cascading effect on these Redis calls. So these are operations that happen in sequence. And so this is potentially an opportunity to optimize this by having these operations operate in parallel or concurrently. So just from this view alone, we can see different patterns that are interesting in our trace, ways to optimize our processing and our transaction, and we can actually drill into them. So one thing I want to point out is that this parent operation, the driver find nearest, which is the light beige node, is quite long relative to any given child it has, but its length encompasses all of the children. So this is a very common relationship in tracing where you have a parent span that encompasses its children. In this case, the children are in sequence, so it's longer than any of them. If we were to make those parallel, we would shorten that parent and then therefore most likely optimize that aspect of the trace. Okay, moving on. So this is what we see if we click on one of these rows. So this is the MySQL operation. We see span tags, we see process tags, and we see log messages. This can be a way to go from that timing information to drill into the metadata that's associated with spans. So here we have the span tags. We see the database query. So we can determine from this maybe we're missing an index or we need to add an index. We have some other data that's there. We can also add additional data. If we have an error, we can annotate that. And then down here we see log messages, which are time-based key value pairs. We see at the very beginning of the span that we're waiting on a lock, and then we acquire the lock about 280 milliseconds later, so there's lock contention. So this can also be an opportunity for an optimization. So this is looking at one trace. It's kind of like a granular view. It's almost a window into the raw data. And there's very little data here that's derived data. So this is just kind of primarily the raw data. So what do we learn from this? We learn in my opinion, sort of traces are like narratives. They kind of give us a sense of a sequence of operations. There's a lot of causality in these traces, and there's a lot of happens before. So the siblings on the Redis call, that kind of sequence of Redis calls, that would be happens before, but there's not causality because they're siblings. But their parent would have a causal relationship with those children. And so traces are a way to isolate a transaction, view the causality, and this gives us substantial visibility into a distributed system, because without this, we have to piece all of this together via logs, maybe Grafana, and that's kind of a heroic effort. So there's some downsides. The downsides are this is a single transaction. So it's a very isolated view of the system. Additionally, traces can be extremely information rich. We have traces that are over 500,000 spans. So then when you have to deal with that, like how do you root cause something? It's a window into a system, but there's just so much going on, it's difficult to focus on. So another approach to viewing tracing data is to compare one trace against another trace. We call this trace comparison or trace diffs. Here's an example of a structural diff. So these are two traces. They're both post orders to eats, and this view is essentially a unified diff. We have a trace A and a trace B, and underneath it we have a tree representation, and we've kind of created a unified diff. One thing to note about this tree representation is that it's a condensed view of the trace. We can see that there's a little over 500 spans in each of these traces, and there's definitely not 500 nodes in this tree. That's because we collapse spans. So if you have service A calling service B, that's actually 3 spans. You have the service A, then you have a client span for the downstream call, and then you have a server span for the request processing. So that way you get a sense of how long the client waited and how long it took to process a request. You can see network latency or whatever else might be contributing to that differential. So we collapse that client span into the parent, so instead of having 3, you end up with 2. Additionally, if service A calls service B 4 times, we collapse that into just service A calling service B, and we associate a count of 4 with service B. So if we look at some of the details of the diff here, we have these gray nodes. These are nodes that are common to both services, and they have the exact same counts. Down here we have these dark nodes, dark red and dark green. These are nodes that are only in one of those traces. So dark red means it's not in trace B. Dark green means it's only in trace B. And here we have light green and light red. Light green means it's in both traces, but there's more in trace B. And light red means it's in both traces, but there's fewer in trace B. So if we look at this trace, we can see that there's kind of a few things going on. We have this gray area in the kind of top sort of center or left aspect of it. So they're kind of on a similar track. Then they have some kind of divergence a little bit near 3, and then things just totally diverge down in this area near 4. So we can see that we have two requests that are similar. They get some noise, and then they just totally branch out. So what's really going on here is these post orders are being processed, and then they check the user's credit. And the user doesn't have credit in trace B, so it rolls back the trace, each order, and trace A continues. So if we were to dig into trace B, this is what it would look like, and this is how we determine that. We have a stack trace that says you have an outstanding balance. So this is some benefits that we can get from trace comparison and also from tracing in general. And I should note that the stack trace and the notes, the annotations on the previous slide about the query and the lock contention, that's all from quality instrumentation. So you get a lot of information for free when you use frameworks that are instrumented, but if you want this level of detail, very often you have to do some special work. Okay, there's another way to compare 2 traces that we've experimented with, and this is to account for trace durations. Here we have, if we look at this unified diff, we have a lot of gray nodes. There's some green and some red, but for the most part, these are very similar. And these have similar number of spans, around 500 in A, 526 in B. So if we look at, so that's similar. If we look at trace B, we can see that it takes about 2.74 seconds to finish. If we look at, or trace A, if we look at trace B, it takes 4.2 seconds to finish. So there's a 50% increase in duration, even though these have very similar structures. So then we're kind of wondering, okay, where is this time going? One of our thoughts might be that it's going to the difference in the 2 traces. So this green section is only in trace B, so we might be thinking, okay, that accounts for the latency. Maybe this is not an optimized sequence. Or we might be thinking, maybe this duration is kind of dispersed throughout. B is generally slower, and that could be a contributor. But if we switch to this view, which is a comparison that's based on the average duration of spans in each of these nodes, we get a different story. So these gray nodes indicate that the durations of the nodes, the spans in the nodes are very, very similar. These white nodes are the section where they don't have anything in common. So the green nodes from the previous slide were only in B, so they're rendered white here because we're not really doing any comparisons there. If we look over here, we can see this dark red node. That means B is slower there. It makes sense too because it's the root node, so naturally the duration's higher, so it's dark red. If nodes in B were faster, then they'd be green. And their darkness is based on sliding scale. It's a heat map, essentially. So we can follow the sequence of what's slower here. We can see that trace B is definitely slower by the virtue of the dark red root node. We can see that the children there's only one red child node. And it's, so we have a highly concentrated sort of source of latency there. And then we can see it has mainly one child is slower, but there's a couple more that are also slow. So the notion that it's, we have to verify that it's not this white area because we're not doing any comparison there. But we can see that we have very strong actors in this few isolated nodes here. So if we mouse over this node, we can see that Wizardly Omega took an extra second. So that's like most of our time. We can see this node below it took an extra 218 milliseconds. So we can really kind of debunk this notion that it's the structural difference that accounted for this duration difference. And we also can see clearly that the difference is not spread throughout, it's highly concentrated. But there are some downsides. Well, actually, we'll go into the good stuff first. So this is a very focused view on structural comparisons and duration comparisons. As such, we filter out a lot of information. Additionally, the tree structure that we're using is a very condensed representation. There's a bunch of different ways to do it. This is one way to do it. We have a GitHub ticket that kind of goes through different options. But that simplification, I think, makes the view more intuitive. And then also, we're emphasizing the differences here. We're doing the structural difference, the latency difference. This focus facilitates the comparison. And lastly, we're doing structural differences which are distinct from the latency comparisons. So kind of focusing on an individual comparison, I think, also simplifies the view. So we've been really after kind of reducing this sort of too much information kind of phenomena. So some downsides are these traces are individual traces, and as such, they can still be outliers. So we may or may not be looking at something that's representative of our system. And as such, they tell us nothing about the population of traces. And so what that means is the user kind of has to validate that themselves. This puts a lot of demand on the user because they have to verify, okay, I'm not looking at a trace that's an outlier, or of these two traces, they're fairly represented. So that means they have to look at a number of traces and kind of get a concept of how different they are to be, to basically get a sense of the context. And that's tough, and especially during root causing. So we can take another approach. We can compare one trace against many. The way we can do that is we can aggregate the many traces and then compare the trace against that aggregate. So this is an approach, an experiment we've done to use that approach with root cause analysis. So here at the top, we have our top level outcome in the service name and operation. So you'll notice there's a request area and a response area. This instance doesn't have any data there, but very often it does. So if you were to expand those, you would get the headers and body of the request, and the body of response time and the status code of the response. So we can kind of see the top level outcome. And then if we look to the right a little bit, we have the link to the Jaeger trace, the timeline view. That's if you want to drill down. Okay, in this area we have a very similar structure to the trace diff, where we condense the trace, and we now represent it with white and dark gray nodes. So these dark gray nodes are nodes that are present in our aggregate, but they're missing in the trace. And the white nodes are the trace itself. So if the trace has a node that's not in the aggregate, we just render it white. It's kind of a simplification. And then if there are nodes in the aggregate that are not in the trace, that were our primary trace, then we render it dark gray. Kind of shows us what's missing. So if we look over here, because we're doing root cause analysis, we're interested in error information. We filter out a lot of the span tags and the metadata and et cetera, but we focus on error data. So here we're mousing over a node that has a red outline. The mouse over shows us that a red exclamation mark with the number 2 next to it. This lets us know there's error data associated with this node. So if we click it, we get this section over here. We call this the error data details panel, error data panel. At the top, we have the service name and the operation name. Then we have span data underneath it. This has 2 spans, so there's a span 0 and a span 1 further down. And these are making calls to Redis. So we know from this node that the error information is associated with a particular downstream. The nice thing about having the error on the upstream is if the downstream's not even there, we still have error data about it. So here we have some, like a log message that has some error details. Could have a stack trace, could have a bunch of stuff. And this is also related to the quality of instrumentation. And then further down, we have a retry. So this node tried to call Redis once, got timed out, tried again, got another error. So this is a way to do a comparison of one to many, and also to surface relevant details based on our usage context. So what's different about this? We now have a concept of how a trace compares to a population of traces. Additionally, we've focused on root cause analysis here. This helps us in a couple different ways. One, we can filter out a lot of information. Like we clicked on that node and we got some error data. If you click on the other nodes that don't have the red exclamation mark, you get nothing. There's no details. So we've really filtered out quite a lot. And this actually helps users, I think, quite a bit. They don't say it helps them, but I think it does. And then because we've focused, we can clarify when to use this, why to use it, and how to use it. And that last part is the simplification stuff. So all of these things make it more approachable to users. And in a large organization, as I've observed, that's actually a big part of actually getting value from your tools. You can build a great tool, but if no one knows about it or if you haven't evangelized it, it's not going to get traction unless it's kind of unique or special. And that's sort of, this facilitates that aspect of it. So now I'm going to turn it over to Yuri, who's going to talk about many-to-many.
Thanks, Drew. So So this root cause analysis technique that Joe described sort of helps, definitely helped us in like expediting the root cause analysis in production outages, right? This is mostly based on the visualization. This is kind of one of the key part of it, plus some aggregation logic. There are other ways of obviously looking at trace populations in a more numeric way and a more exploratory way. This is like kind of custom built tool that is very specific, that we thought that would bring a lot of value to the company, and so we built that in a very specific way. But let's talk about kind of other ways, right? So if we compare now two groups of traces, maybe we want to see I don't know, some trends in them, some like numerical differences which are not necessarily visual differences, right? And what is the common way of doing that? Well, kind of the workflow is kind of very simple. You basically extract certain features that you think are interesting about the trace. It could be like in the example of a trace that Joe showed, like what is my self-duration for a particular service, right, within the trace? Like how much percentage of the time my service is on a critical path, as could be one example. And then you extract that feature, you kind of aggregate that feature across many traces. You build a population, you build summaries, and then you compare summaries. You compare summaries between one population and another. You have to be careful with statistical significance of that, because if you making deductions about saying, oh, like I'm seeing 10% regression in, let's say, latency, well, you have to be careful whether, especially with the sampling that happens in the tracing, it's not always like clear cut of whether your numbers are actually relevant, right? But assuming that they are, maybe you have enough sampling, then how you do that. So I'm actually going to talk about other things that other companies did in the space. So specifically at Pinterest, Pinterest have a tracing system called PinTrace. It's not like shown on the left side. It's like I'm not even showing the whole system. But let's say we assume that there is some tracing infrastructure, right, which collects tracing data, and they use streaming based on Kafka. And so those Kafka streams come into a storage, let's say in Elasticsearch, and get stored. And then the trace analyzer part of that system is kind of the new thing that does the aggregation. So it starts with like a UI, Jupyter Notebook in this case, where the developer can specify certain parameters, things like select from this particular range. It's basically some selection criteria for population of traces, for two populations of traces actually, right? And then those criteria get pushed into a Spark job, which continuously running against the data, and the job just like calculates the summaries and stores them into reports, and you get back to the engineer. And so this allows you slightly like more exploratory analysis, because you can vary parameters for which you're querying, right? And the thing that you can specify as inputs are like different time periods. You can select maybe different modes of the phones that the users are using, whatever. There's like a lot of different ways of you can filter that. And then the benefits are, or examples of comparison, we can look at what's, like I said, the average duration of time of the critical path, number of calls, and these are the things that the trace analyzer has actually built in already. So these are features that are automatically extracted by the pipeline, and you get the summary, and then you can look at those summaries in like across the timeline. And so what types of analysis they can do with that is like you can construct a latency histogram for one period versus another. You can overlay them and see whether your latency histogram is actually different. Maybe you got a separate mode of the latency distribution somewhere, right? You can observe trends. If you are observing, let's say, how much my service is on a critical path, last month versus this month, or previous release and versus this release, you can potentially see degradation in that, and so take actions as well. One of the interesting thing about sort of doing this kind of aggregate analysis is that you capture interesting traces as part of the populations, and so you can actually go back to them and drill down into this like swath of raw data that Joe showed, like whether you can have a trace with 100,000 or 500,000 spans. So hard to use, but in this case, you actually know what that trace represents in your population, in your specific analysis. So you kind of get a signal already that this is something that I should look at. And so then you go into the trace view and like drill down into what's going on with there. And also, like if you're doing trends, you can also start building alerts on top of that. And so again, when we think about alerts, it sounds like, well, why wouldn't you just use metrics for alerts, right? But again, we're talking about here specific features that can only be extracted from tracing information, right? Things like how much time I spent on a critical path in this service. This is not something you can get from any metric system. You have to analyze the trace for that, right? And so there's lots of features like that, or like how many times service A called service B, right? So with a particular, like some other filtering conditions. So those things are difficult to get with any other monitoring tool, but with tracing you can, and then you can start actually building alerts on top of that, because they kind of give you the time series in the end. The challenges in that approach are that even though, I mean, it's a bit like hard-coded, right? So you can vary the input slightly to select the population, but the feature extraction itself is mostly static, at least at the time when they presented this. They may have done better now. And those feature extractions, they're built by the central tracing team, kind of similar to what our trace diffs that our tracing team built that. And so it's good if it works, but in many cases, like you don't know a priori whether this particular thing is useful or not to people, right? And so if someone says, well, I want to run this particular experiment with this new feature, well, how would I get it? And tracing team needs to get involved and to develop it and deploy it, right? So it's like, it's hard to scale the tracing team in that way to do exploratory analysis across like thousands of engineers in a company. And so like the general solutions get you only so far. Like if you got lucky and hit the point, then great. But if it's like maybe more general, it may not be as useful, right? And so with that in mind, we come to another approach, which is done by Canopy at Facebook. There was a paper published earlier this year where the feature extraction is kind of also built directly into the tracing infrastructure. There's always like a real-time pipeline working on all the tracing stream and extracting features and storing them in an analytical database. They have Scuba, which allows you to then, once it's an analytical database, you can like issue all kinds of queries and filter by dimensions and build all kinds of histograms and time series. Is very like rich data sets. And here the main difference is that they kind of allow you a lot more exploration because technically developers could write new features into that pipeline. And rather than like building canned reports, they give you the ad hoc analysis ability. And the main focus is, again, it's like on the derived data. You're not processing raw traces, because like raw traces are so rich and so overwhelming to most developers, it's like almost impossible to get anyone to look at like a trace view. But by looking at the aggregates, actually, you get signals that kind of make sense to people, right? So, and one observation that the paper makes is that no one really cares about every single detail in the trace, and so by allowing people to focus on like on specific parts of the trace is like really enabling people to investigate problems in the systems. However, there is still a challenge here is that even though that feature extraction is technically extensible, developers could build new features. This is kind of still high friction process because like in order to build a feature, you kind of need to understand well that the detailed trace model. You need to technically deploy it in production, right? So you have to develop, you put it into the real-time pipeline. Probably tracing team still needs to get involved to at least approve your pull request to enable that thing. So it's still a bit high friction, and so. That's another thing that Facebook does. They gave a talk at our tracing meetup that we run in New York City, and they talked about like a next evolution of that thing that I really liked is that even more ad hoc analysis and enabling developers to investigate even more on their own without actually central team getting involved in building feature extractions. And the way that works is kind of very neat. They started saying, okay, we're gonna go with Python notebook because there's like a lot of data scientists like that, and it's like kind of very easy to explore data using that. And then, so you write a certain code in Python. It could be like based on like known data science frameworks like Pandas or whatever. Plus, obviously, tracing team provides a certain framework how you get the trace data into a certain model, how you can navigate that model, right? Once that's in place, then it's up to the developer to say, okay, well, I think this feature would be very useful for me to extract from the traces. So let me just write a quick code. It's like a query, maybe a few lines in Python, to walk the trace and figure out this feature, right? And then what I especially like about the approach is that they said, okay, well now I've written this code. How do I actually test it? How do I make sure that I'm getting enough signal, and how do I put it in production? And the point was like, well, let's use the same code over, right? Rather than keep redeveloping it. And so like in Python, then in Java, in in the pipeline or something, it's very hard. And so instead, this is kind of the benefit of the Python notebook, is that you can run it on a small data set, maybe like a few dozen traces, how much fits in your memory, basically, to develop that feature extraction algorithm. Once you have it, you move to the next phase, you run it across a large set of data, or like historical data with like some query parameters to select the population, and then you iterate on that, and maybe you say, okay, you know what, I'm really getting a very strong signal about something that's very useful to me. By like, I've developed that feature extraction, which really gives me a very signal about like, oh, my service is misbehaving, no, this is the root cause. And once you have that decision, then you simply take that exact same code and you just migrate it to the real-time pipeline, and you start getting that feature extracted in real time and basically stored in some analytical database where you can start doing time series analysis on it, like filtering, partitioning, etc. And so this is, I think, again, is a very interesting approach that that they took. And the main thing is like the tracing team is definitely always often like a bottleneck for these explorations, because we've seen that in Uber as well. We had another team which was like a performance team, and they had all these kind of ideas about, oh, we can use tracing this way and this way. And then every time they wanted to try it, well, it takes them like 3 months to build an infrastructure, because like, yes, you can do that, but we have no platform to actually do this ad hoc analysis on a high scale, right? And so, and many of their ideas didn't pan out because, yeah, they thought that it was a good idea, but in the end, it was like, the signal wasn't that strong in the end, right? And so by enabling teams to actually help themselves by sort of like enabling this ad hoc analysis infrastructure opens up a lot of powerful analysis on the tracing data. And also, like rather than tracing team building something which, like, I don't know how all 3,000 services at Uber are working, right? So they have very specific things that they know about their service. Maybe they even put some specific instrumentation in their service that they want to extract as a feature. And so the enabling teams to do that is very powerful. And my team, the platform team for tracing, can actually focus on the platform. It's like making it higher, more scalable, making this query language, the domain model, etc., more powerful, etc. The slides froze. Didn't we have like one last slide? Oh no. All right. So I guess we had a Q&A slide, but this is the time for Q&A. I think we have time. Yeah.
Any questions? We only have one microphone. This is going to be hilarious. Yeah. Maybe you can shout the question out and we can repeat it.
I understand you were surveying what different organizations have done, but it looked like some of the stuff at the beginning was features that had been written in Jaeger. Is that right?
Yeah, so the trace will. Oh, sorry. The question is, so I surveyed kind of techniques, and Joe and I surveyed techniques across multiple like companies, right? And whether some of these things were built into Jaeger, that's the question. So the trace diffs that we presented in the first half, they are part of Jaeger, right? And so the diffs of like many to one, so there is certain analytical framework, aggregation framework, that's not part of Jaeger yet. It's like internal at Uber because it's specific to how our infrastructure operates. But yeah, the basic visualizations for the comparing traces, that's already in Jaeger. Yeah, the duration I think is like still in a work in progress. It's a pull request. We also have like some other people using that same visualization already to render traces as a graph. Also pull request there, so it's like very promising area seems to be.
Oh, we got another microphone.
Thanks.
Cool.
Hi. So the extracting features and letting teams analyze the traces themselves is really cool. Have you found that they focus on like their own service, or like, you know, if the problem is due to like interactions between multiple team services to like get together and work on it? Like, how do you find that empowering teams helps in situation where like coordination is required across multiple teams?
Okay. Yeah, I cannot really claim expertise yet on that because we just started this and we don't have internally that ad hoc analysis platform. I think there are two parts to that. One is even with Facebook ad hoc analysis, they still say that there is a value in like predefined standard reports, that common reports that everybody can use, that extracts like features that are useful to most service owners about the particular service, right? Like with experience, they kind of accumulate a number of features that are useful. And so because if you're a developer who never really used tracing before and you want to come to that, it's like very overwhelming to start using tracing, right? So it's like using common reports is actually a very good way to start because it shows you some trends that you can already see, and then maybe once you found anomaly in the trend, you can drill down into a sample trace and say, oh, well, let me investigate, and now I can understand better what's going on here, right? And so, the first part of your question is like whether it's like one team for one service or across the services. I think that depends. It can be both because I've seen at Uber experience that people were using tracing to just optimize their own service, right? To understand how their downstream systems behave and how they can call them more efficiently or something like that. And we've also seen tracing being used by like SREs, and we have like an organization called Ring Zero, which is sort of like first responders to major incidents that involve like specific business workflows being affected. So those teams, they definitely don't own most of the services, so they look at the high level, and so they extract, if they were to extract features, I would assume those would be like across multiple services.
One more quick question. I really like the visualizations. Do you see any value in looking at the latency and structural differences together, or do you think that's too much complexity to kind of show people at the same time?
I think, do you want to take that?
Yeah, sure. Yeah, I think that could be really interesting. We haven't done that primarily because we want to kind of roll it out, get a sense of it, and then see how users respond to it and how much it resonates. I think that type of combination could be very powerful, as well as other combinations, such as looking at self-time, client span duration versus downstream server span durations, visualizing that. So I think that these are sort of the kind of MVP visualizations, and then what you're talking about would be maybe the next evolution. But then potentially, one of the benefits is it's approachable. So kind of maintaining that approachability would be one of the challenges with taking it further.